All right, let's jump right in. Today, we're going to tackle one of the absolute cornerstones of physics, motion in a straight line. And trust me, by the end of this, you're going to have all the tools and the confidence you need to absolutely crush these problems on your exams. Welcome to Microscopic Marvels.
Hello, NEET and JEE aspirants.
Okay, so let's kick things off with a simple question. Picture this. You're in a car, you look down at the speedometer, and it reads 80 kilometers per hour. So what does that number really mean? Is that your average speed for the whole journey? Or is it something else entirely? This one little question, you guys, it gets right to the very core of what we need to nail down today. Now, to answer that properly, we've got to make sure we're all speaking the same language, the language of physics. So let's start with the absolute basics, the bedrock for everything we're about to discuss. You know, the universe is just full of all kinds of complicated motion, right? But in physics, especially when you're gearing up for exams like NEET and JEE, we always start with the simplest case first, and that's rectilinear motion. All this means really is that we're looking at objects moving in a perfectly straight line. You have to master this first, because it's the foundation for literally everything else in kinematics. Okay, here's a really cool trick we use all the time in physics. Think about a car driving from one city to another, hundreds of kilometers away. Compared to that huge distance, the car itself is just a tiny speck, right? So we can just treat it as a single point. It's called the point-object approximation, and it's this super powerful tool that lets us simplify some really complex problems and still get the right answer. All right, let's keep building on this. We're going to circle right back to that car question now, because it's kind of tackle a concept that, honestly, trips up a lot of students. I'm talking about the super important difference between two types of velocity. So you've got two main players here. First, there's average velocity. That's pretty straightforward. It's just your total displacement divided by the total time it took you. Simple enough. But then you have instantaneous velocity, and that is the answer to our question. That 80 kilometers per hour on the speedometer, that's not your average. It's your velocity at that one specific instant in time. Okay, so how on earth do we actually calculate that instantaneous velocity? Well, imagine you're calculating the average velocity, but you do it over a really, really tiny time interval. Now, what if you make that interval even smaller, and smaller, and smaller still? As that little slice of time, delta t, gets closer and closer to zero, you're essentially zooming in on a single moment. And bam, you found the instantaneous velocity. That's the limit definition right there. But you know what? There's an even better way. This is where calculus becomes your best friend. Instead of all that shrinking time interval stuff, we can use a super elegant tool, the derivative. We just say that velocity, v, is the derivative of position, x, with respect to time, t. Seriously, for your exams, v equals dx over dt is the definition you need to know. It's powerful, it's precise, and it's how you're going to solve these problems. Okay, cool. So velocity is how fast your position is changing. Makes sense. But that leads to the next big question, right? What makes velocity change? What's the engine behind that change? Well, let's meet our next key player, acceleration. The logic here is exactly the same. Just like velocity is the rate of change of position, acceleration is simply the rate of change of velocity. Now listen up, because this is a super common mistake. A lot of people think acceleration only means speeding up. Nope. When you slam on the brakes in a car, you're also accelerating. We just happen to call it deceleration. The key takeaway here is this. Acceleration is any change in velocity, period. And you know, we can actually see this on a position time graph. It's pretty cool. If the graph is curving upwards, kind of like a smile, that's telling you there's positive acceleration. If it's curving downwards, like a frown, well, that's negative acceleration. And what if it's just a perfectly straight, sloped line? That means zero acceleration. The velocity isn't changing at all. It's constant. All right, we've covered the basics. We've laid all the groundwork. Now it's time for the main event. What's coming up next is your ultimate toolkit. These are the equations that are going to let you solve like 99% of the kinematics problems you'll ever see. First tool in the box, V equals V naught plus AT. So when do you pull this one out? Simple. This is your go-to formula anytime a problem talks about velocity, acceleration, and time, but doesn't mention displacement at all. If X is missing, this is your guy. Okay, tool number 2. x equals v0t plus half at squared. This one is going to be your best friend when the question is all about finding displacement, and you've got the initial velocity, time, and acceleration, but you have no idea what the final velocity is. If v is the mystery, use this. And the last of our big three, v squared equals v0 squared plus 2ax. I personally like to call this the timeless equation. Why? Well, just look at it. There's no t for time anywhere in sight. So if a problem gives you displacement but leaves out the time, this is the equation you'll want to use. It's a lifesaver. So here they are, all three together on one slide. Your complete kinematics toolkit. You absolutely have to memorize these, and more importantly, understand when to use them. But, and this is the most important part, there is one golden rule you can never forget. These equations only, and I mean only, work if the acceleration is constant. If a is changing, you can't use them. Forgetting this is a super common way to lose marks on the exam, so please lock this rule in your brain. Look, knowing the theory is one thing, but the real test, right? It's being able to apply it when the clock is ticking. So let's take our brand new toolkit for a spin and solve a classic exam-style problem together, step by step. I want to give you a simple 4-step method that you can use every single time. It's foolproof. Step 1, set up your playing field. Define your origin, and most importantly, decide which direction is positive and which is negative. Getting your signs right is everything. Step 2, take inventory. Make a list of all the knowns, the stuff the problem gives you, and the unknowns, what you're trying to find. Step 3, choose your tool. Look at your list and pick the kinematic equation from our toolkit that fits perfectly. And finally, step 4, just plug in the numbers and solve. That's it. All right, let's try it out on a classic, the stopping distance problem. So a car is moving and then brakes to a stop. Step 1, let's say the direction it was moving is the positive direction. Easy enough. Step 2, what do we know? We have an initial velocity, v0. The final velocity, v, is 0 because, hey, it stopped. We're told it has a constant acceleration, a, which will be negative since it's slowing down, and our unknown is the distance, x. Okay, step 3, we have v, v0, a, and x. No time. Which equation is that? That's right, our timeless equation. V squared equals v0 squared plus 2ax. Step 4, we plug in 0 for v, do a little algebra to solve for x, and boom. We get x equals negative v0 squared over 2a. See? The method just works. Okay, before we finish, I have to share a huge, massive exam trap that you need to watch out for. Please listen carefully. A negative sign on acceleration does not always mean the object is slowing down. Think about it. If you drop a ball and you decide that down is the negative direction, then its velocity is negative, right? But gravity is also pulling it down, so its acceleration is also negative. Both are negative, but the ball is definitely speeding up. So here's the real rule. If velocity and acceleration have the same sign, both positive or both negative, the object speeds up. If they have opposite signs, it slows down. That's it. It's all about their relative direction.
If you found this video helpful, please like, comment, and subscribe for more NEET and JEE physics content.